Welcome to the course on DC motor modeling and state estimation using a linear Kalman filter, presented by kalman-filter.com. Please subscribe to this channel. Here is an overview of today's presentation. We will begin with an introduction, followed by the continuous time system model, which includes both the electrical and kinematic system models. Next, we will explore the combined state-space model and discuss its observability and noise determination. After that, we will delve into the discrete time system model. Finally, we will cover the implementation and results, and conclude with references. In this course, we will focus on estimating the angular position, angular velocity, and armature current of a DC motor using a linear Kalman filter. While nonlinear models offer greater accuracy, for educational purposes, we will utilize a widely accepted linear model that is sufficient for our analysis. Let's begin by discussing the continuous time system model of a DC motor. The modeling process is divided into two main components, the electrical system and the kinematic system. Understanding both parts is essential for accurate state estimation. The electrical system of a DC motor comprises the armature resistance, denoted by R, and the inductance of the armature winding, represented by L. These are connected in series with the electromechanical energy converter, which is the DC motor itself, labeled as M. This entire circuit is powered by a voltage source, V sub S. Here is a visual representation of the electrical system model of a DC motor. Using the mesh equation, we can derive the following relationship. The supply voltage V sub S equals the inductance L times the derivative of the armature current, plus the resistance R times the current, minus the induced voltage V sub E. The induced voltage is linearly related to the angular velocity, expressed as V sub E equals the motor velocity constant. K sub E times the angular velocity theta dot. By rearranging the equation to solve for the derivative of the current, we obtain a first-order differential equation that will later be incorporated into our state-space model. Moving on to the kinematic system model. The mechanical behavior of the DC motor is described by the physics of rotations around a fixed axis. We assume that the mechanical shaft and the actuated load are combined into a single angular mass, denoted by J. This simplification allows us to model the system more effectively. Here is a diagram illustrating the kinematic system model of a DC motor. The relationship between angular acceleration and torque in the DC motor is given by the equation J times theta double dot equals the motor torque M sub, M minus the friction torque M sub, R minus the load torque M sub L. The motor torque is directly proportional to the armature current, expressed as M sub M equals the motor torque constant K sub T times the current I. The friction torque is proportional to the angular velocity, with M sub R equal to the coefficient B times theta dot. The load torque M sub L is assumed to be zero if the motor operates without a payload, but we will later consider it as an unknown quantity. Solving for the angular acceleration theta double dot, we obtain a second-order differential equation. By combining the electrical and kinematic differential equations, we can form a comprehensive state-space model of the DC motor. We define four state variables: theta, theta dot, the load torque M sub L, and the armature current I. The state space representation includes the system matrix A, the input matrix B, and the disturbance matrix G. Additionally, we define the input as the voltage supply V sub S. The measurement equation relates the measurable output to the state variables, allowing us to estimate the system's states using a Kalman filter. Here are the state space matrices for our DC motor model. The system matrix. A captures the dynamics of the states, including the relationships between angular position, velocity, load torque, and current. The input matrix B represents how the voltage supply influences the system, while the disturbance matrix G accounts for the unknown disturbances affecting the load torque. The measurement matrix C is designed to measure only the angular position theta. The measurement equation is a crucial part of our model. It states that the measurable output y equals the measurement matrix C times the state vector x, plus the measurement noise v. In our case, we assume that we can measure the angular position theta directly using an absolute encoder. This results in a measurement matrix C that selects the first state variable from the state vector. A few important notes on our modeling approach. The selection of state variables is flexible, and alternative choices can be made based on different modeling preferences. We have modeled the load torque m sub L as an unknown and noisy disturbance, assuming that its derivative is mean-free. This allows us to include the load torque as an additional state variable in our state space model, facilitating more accurate state estimation. Next, we transition to the discrete time system model. We utilize specific parameter values for the angular mass J, friction coefficient B, motor torque constant K sub T, motor velocity constant K sub E, armature resistance R, inductance L, and the sampling time T sub S. Discretization of the continuous time matrices A and B is performed using the matrix exponential and integral methods, respectively, to obtain the discrete time state and input matrices, A sub D and B sub D. In discrete time, the state vector at time step k equals the discrete system matrix. A sub D times the state vector at the previous time step, plus the discrete input matrix B sub D times the input at the previous time step, plus the disturbance matrix G times the disturbance at the previous time step. Similarly, the output y at time step k is given by the measurement matrix C times the current state vector plus the measurement noise. Focusing on the load torque, we model it as a random walk. Specifically, the load torque at time step k equals the load torque at the previous time step plus a Gaussian noise term V sub ml. This approach treats the change in load torque as a stochastic process, allowing our model to account for unknown and varying external loads on the DC motor. Ensuring that our system is observable is essential for accurate state estimation. We construct the observability matrix by stacking the measurement matrix C and its successive multiplications with the system matrix A sub D. In our case, the observability matrix has a full rank of 4, which matches the number of state variables. This confirms that our system is fully observable with the chosen measurement mapping, meaning all states can be inferred from the measurements. Let's discuss the process noise in our model. The process noise covariance matrix Q is defined with a variance of 2.25 times 10 to the negative 6 for the load torque state, while all other elements are 0. To obtain the discrete process noise covariance matrix Q sub D, we perform an integration involving the system matrix A and the continuous process, noise covariance Q over the sampling interval. However, the exact calculation of Q sub D is complex and not provided here. Regarding measurement noise, we base our assumptions on the specifications of an absolute encoder with a 12-bit resolution, which provides 4,096 discrete position measurements. Each position increment corresponds to approximately 0.088 degrees. The variance of the measurement noise is calculated to be 1.96 times 10 to the negative 7 radians squared. This low measurement noise variance indicates high measurement precision. Moving on to the implementation and results, we conducted simulations using MATLAB. To simulate realistic operating conditions, the input voltage to the DC motor is set to 6 volts initially, and then increased to 12 volts midway through the simulation to mimic controller action. Here is a graph showing the input voltage over time. In this slide, we compare the estimated states to the ground truth obtained from the simulation. The first state, theta, the angular position, is shown alongside its measurement. The second state, theta dot, representing angular velocity, is compared with an approximate derivative of the measurements. Additionally, we display the estimates for the load torque and armature current. Overall, the estimates closely follow the true values, demonstrating the effectiveness of the Kalman filter in state estimation. We now examine the root mean square error, or RMSE, for our state estimates. The RMSE for the first state, theta, aligns closely with the RMSE of the measurements, which is expected given the low measurement noise. For the second state, theta dot, The RMSE experiences spikes when there are abrupt changes in the input voltage. This highlights the challenges in estimating angular velocity solely based on derived measurements without a state estimator. Finally, we assess the normalized estimation error squared, or NEAS, to validate the accuracy of our simulation. We performed 1,000 Monte Carlo simulations and established a 95% confidence interval ranging from 3.83 to 4.18. The NEAS values remain within this confidence interval, and the mean NEAS is close to 4, which corresponds to the degrees of freedom of our state space system. This indicates that our state estimates are statistically consistent and reliable. To conclude, I would like to acknowledge the textbook by Yaakov Bar Shalom and colleagues titled Estimation with Applications to Tracking and Navigation, Theory, Algorithms, and Software, which serves as an invaluable reference for this course. You can find it on Amazon through the provided link. Thank you for your attention. Please follow this channel and visit kalman-filter.com for more educational content on Kalman filters and state estimation. If you have any questions or feedback, feel free to leave a comment below. Have a great day.